My name is Markus Hauck. I'm from Codecentric, and today I will present you a talk about free monads and free applicatives. So quickly, what this is talk about. We will write a DSL using free monads, and then we will switch to free applicatives. We will explore the specific pros and cons using each of them. Then we will show you how to optimize our DSL during execution using free applicatives. And at the end, we will combine free monads and free applicatives. So before we start, what do we need for this? We need a functional programming library of our choice. In this talk, I will use cats, but you could use Scala Z as well. And our plan, as I said before, is to use a DSL to query the GitHub API. The first version will use only the free monad. The second version will only use free applicatives, and at the end, we will be using both. So as a quick reminder before we start, there is a cool plugin for SBT and Scala called KindProjector, which basically allows you to write type lambdas like this, where you have a type lambda that takes an argument A and returns constantly an int, and at the value level that is equivalent to just taking any argument and returning the 42. And we have this question mark, which is the same as the underscore on the value level. So what do we want to do? We want to query GitHub, and we want, given an owner and a repo, we want to list all issues, here highlighted in blue. For the issues, we want to find all of its comments. You might know this issue. And then for every commenter, we want to get from the login name, like Markus 1189, to the full name if it's given in the profile. So first, to start, why bother with free applicatives or free monads at all? Why not just write functions like this, where we take as an argument the owner and the repo for list issues, and then return the future hitting the network? Well, first of all, we are limited to this one interpretation, which means we can only do this using futures, so it's asynchronous. We cannot do it without it. It's hard to test this without hitting the network. And we have no control from the DSL author perspective, which we will see in a moment why this is important. So let's start with free monads, because they allow each of these concepts I described now. What we will not cover is having different interpreters, like, for example, we have one that is pure and only hits a key value store in memory, and one that actually hits the network, which is quite nice for testing. But what we will cover is the steps to write a DSL. And for this, it's basically always the same 3 steps. You first have to write your instructions as an ADT. Then you use the free monad to lift them. And finally, you write an interpreter to give semantics to your DSL. So first step, we write our instructions as an ADT, as I said. We take a type trait GitHub with a type argument. And then for each of our operations that we want to perform, we have a case class, taking as constructor arguments the parameters we require. And we return a type of type GitHub of the respective return type that we will receive. Okay, that was step 1. The second step is we lift each of our instructions into the free monad. And this is actually the same for all of our instructions. It just differs on the number of parameters. And then we each time call free.liftf to lift our instruction into the free monad, and we get back a result of GitHub monadic, which is a type alias for the free monad over our instruction ADT. You will see in a moment why I call it GitHub monadic, which is a rather long name because it kind of defeats the purpose of a type alias, but we go for that for the presentation. So the next step is we have to write an interpreter. So for interpretation, the free monad already defines a method called foldMap, which I have shown here, and it takes as an argument with the name f this twiddly arrow from S to M. And what this actually is a natural transformation, which is a polymorphic function because Scala does not allow explicitly quantified value functions. And what it actually does is it transforms from one higher kind constructor to another without caring about the contents. It only cares about the shape, so to say. So we now have to define a natural transformation for our interpreter that goes from our instructions ADT to some target type constructor. To make this more concrete, we will just use future, but you are probably off taking something else like the Monix task we have seen before. And what we do is we create a new instance of this natural transformation going from our instructions ADT to the future. And we do this by implementing the apply method there, where we match on our instruction ADT. And if it's a get comments instruction, we call to the underlying HTTP client, which we do not really care about at this point. And we hit the network for the endpoint of the specific instruction. And then we map the response and pass everything into a comment. And now we do this also for the get user instruction and for the list issue instruction. Okay, so with this in place, we can already write our first program. And what we want to do is we want to first retrieve all issues given an owner and a repo. We then want to iterate over all issues, fetching every comment. And then for each comment, we want to get the full name. And we do this in our program here by first calling our list issue instruction with the given owner and repo. Then we traverse over the returned issues, call get comments here for everyone. And finally, we do a nested traversal over the issues and the comments and call get user for each of them. So at the end, we return our users. So we get back a GitHub monadic of a list, which contains tuples of the issue and the comments, which in turn has a list of comment and user tuples. Okay, so we're almost done with our first DSL. What's nice about this is that we can use, as you have seen, the power of the monad. So we can use for comprehensions. We can use monadic if. We can do monadic looping. We can even use predefined functions like group M, which takes a monadic predicate to group on. And our DSL looks quite good because we can use the for comprehension. But there are some disadvantages. Like, for example, what if we want to execute some of this in parallel? Or what about efficiency? For example, with the GitHub API, we have the problem that we are rate limited, such that we are, for example, limited without authentication to 60 calls per hour, which is not very much. So let's try the demo. I don't know if it works. Yes, seems to work. So you don't have to read this. You just have to see we're starting SBT. And we're running our main, we're getting our issues. Then we get the comments from each of them hitting the network. We get a lot of comments. And once we're done with the comments, we start to get the users. Okay, so we will get a lot of those users. And you can also see that we are doing lots of duplicate requests for comments that have the same commenter. So I now step in and take the halting opportunity to skip to the next slide, because it will take a lot of time. And here's another view on our execution. So first, we list all of the issues, and then sequentially, we fetch the first comment, the second comment, and the third comment. And only once we're done with that, we can proceed to fetch the first username, and the second, and the third. So there's no parallelism at all using free monads, actually. So to recap our free monads part, free monads are quite popular currently, and there are lots of tutorials showing you how to write DSLs or make use of them. And actually also the F monad is using free monads under the hood. And what's not so nice about this is that we are forced into sequential execution and there's nothing we can do about it. And what's also not good is that we cannot do any static analysis on free monad programs, because we can only look at the first instruction and the rest is hidden behind the continuation, which you may have seen in the talk from Eric. Okay, so looks like our problem is that free monads are too powerful. So maybe there's the thing called applicatives, which are not as powerful as monads. And looking at our functional programming of choice, programming library of choice, we see there are also free applicatives. So why not use them? So we again have the same three steps. We first write our instruction as an ADT. Okay, we have a check, we already did that. Then we use free applicative to lift our instructions. And finally, we write an interpreter. Okay, we can also make a check mark there because we already did this. So the remaining step is only the second one. And again, we create a type alias for our DSL called GitHub Applicative. And we do almost the same as for the free monad, but instead of using free.liftf, we use freeapplicative.lift. And it's actually the same for each of the instruction again. Okay, so now that we have all of the 3 steps done, we can begin writing programs again. This time we cannot make use of for comprehensions because we do not have flat map. But we can, for example, use the applicative builder to here write a program that retrieves the issues from a repo foo and a repo bar, and then concats the resulting lists to get one list of issue again. Or alternatively, we can also use traverse to traverse the list of users and fetch all of them. So we have quite a lot to express programs, but we're still more limited than with free monads. So what's nice about this now is that we can execute those programs in parallel, because with free applicatives, our effects are independent of each other's. And here I'm kind of cheating because the applicative instance for future already runs in parallel. You might have to use a different type class instance for other types. And we, of course, could now traverse a list of 1,000 logins and have that happen in parallel, only limited by our concrete implementation of the HTTP client or our execution context. Okay, so now we might want to see how that executes. So here is a small program that has a list of repos. And now we traverse this list and we want to list the issues from each of those. And at the end, we flatten the result. Okay, so looking again at the output, if we run this small program, we start SBT, then we run our main, and it does list issues in parallel, and it's already done with all of the issues. Okay, that looked not too bad. But what's even nicer than parallel execution is static analysis of free applicatives. So what this means is then if we fetch the full usernames of a list of users, for example, as in the free monad case, we saw there are lots of duplicates. So if we are rate limited, like for the GitHub API, we may not want to fetch the same username again and again because we are just wasting resources there. So now in the next few slides, I will show you an optimization that eliminates duplicate requests from these programs without that the user has to take care of it. So to do this, there is a method defined on free applicatives, which is called analyze. And analyze takes, again, a natural transformation. And here's also one of the type lambdas, which just constantly returns the m, which has to be a monoid. And we give this natural transformation to the analyze function, and it will return a monoid again. So what we now want to do is we translate each of our instructions from our ADT into one concrete monoid value. Okay, so here's a static analysis called logins, which again is the natural transformation, and it goes from GitHub, so our instructions, to a set of user logins because we want to eliminate duplicates. And we pattern match on our instructions again, and if it's a get user instruction, we return a singleton set with this usernet login, and otherwise we just return an empty set because we do not care about the rest of the instructions. And then we can define a method extract logins that, given a GitHub applicative program of any type, we do not care, returns a set of user logins, which simply calls analyze on the program and passes in our natural transformation. Okay, now that we have this better interpreter step, the natural transformation, we can write an improved interpreter here called precompute first, which is the first step of the improving interpreter. And what it does, it gets a GitHub applicative program as an argument, and the interpreter function, GitHub to F, so it's polymorphic over it, and it will return a map from user logins to user. So what this does is it will first use our static analysis to extract the user logins, eliminate duplicates because it's a set. We will then traverse this list of unique logins and hit the network to fetch the full username. And at the end, we will return the map that associates each login to the corresponding user. And the next step in our interpreter is now to write something called optimize net, which given the mapping from the previous step and the interpreter step that we also pass in, will return a new one that makes use of our mapping that we also now have available. So we again write instance of the natural transformation, and we first look at the mapping. If the user login is already in there, which is the sum case, then we purely return that user without fetching it from the network again. And if we don't find it, we fall back to the normal interpreter, which possibly will hit the network. And for all other instructions, we just fall back on the natural transformation we are passed in. Okay, given that, we can finally define a better interpreter for our applicative programs. So given P, our GitHub applicative program, we return a future of the result. And we do this by just plugging together our steps we have now available. We pre-compute our mapping, and then we flat map over that. We optimize our natural transformation, and finally use that optimized one to interpret our program. Okay, so this was only one possible optimization to eliminate duplicate requests from our programs. It would also be a nice idea to, for example, group requests for comments by repo and then hit the repo only once, fetching all of those comments, because then we can also reduce the number of calls we are doing per hour. And instead of executing everything in parallel, we might also want to limit it by a boundary. For example, we want to batch it up in like groups of 10, and then we could mix parallel execution and sequential execution. And there's many more you can do with this. So that's one of the reasons why free applicatives are so cool currently. And now the interesting question is, are we already done? Well, it turns out it's not that easy with our DSL, because if we want, for example, to first list all issues given on an owner and a repo, and we consequently want to get the comments from those issues, we might write it like that. We just take the issues we list here, and then we map over that because that's actually the only thing we can do. But the result will be a nested GitHub applicative of list of comment. So this already looks monadic, but remember we are just using applicative, so there is no flatten, there is no flat map. So that's actually a problem, because what we want to do requires us to depend on previous effects, which is the single thing that free monads or monads in general are good for. So even for this small program, we are stuck using only free applicatives. Okay, so going back a little bit, we have tried free monads, which were too powerful, and then we tried free applicatives, which were not powerful enough. That's a problem. So let's use something else, because free monads work over any functor. We can make use of the fact that functors compose nicely. So for example, you can nest two functors and the result will be a functor again. Or you can take the product of two functors and it's a functor again. And the same also for coproduct. You can take the coproduct of two functors and it will also be a functor again. So what this allows us, using the coproduct from cats, which is essentially a higher kinded either, where it's either an f of a or an g of a, is to compose our instructions ADT. So what if we use not only our simple instructions ADT, but a coproduct of either the normal instruction or it's already a GitHub applicative program, because applicative are also functors. And now we still do the lifting into the free monad and the coproduct now, so we have to do a little bit more work, but that's kind of boring because it's always the same, so I left that out here. And then we add one important additional operation here called embed, which, given a GitHub applicative program, will embed that into the coproduct and lift it into the free monad. So let's have a look at our to-do list again for writing the DSL. The first step is again to write an instruction. Okay, we already did that, and we saw the embed instruction, which we have now in addition. Then we have to use thrift to lift instruction that we already did at the slide previously. And now we just have to write an interpreter for our new coproduct. And turns out that we already have all the pieces we need. We have our interpreter function for GitHub to future, which is just the interpreter from FreeMonad. We have a natural transformation from GitHub applicative to future, which is our optimizing interpreter, or optionally one that does no optimization. And we still need a natural transformation from co-product of our instruction ADT GitHub and GitHub applicative to future. So luckily, we can use a function that is defined on natural transformation called OR, which will combine two natural transformation into one that works over a co-product of both, which is exactly what we need in our case. So we can define a new interpret function, interpret mix, which is the OR of our normal interpreter and our optimizing interpreter. And what we will get back is the interpreter for our co-product to our future. And then running our GitHub both programs is just a matter of calling foldmap with our new interpreter. Okay, so now back to our program we originally wanted to write for FreeMonads. And using the new style now, it looks like this, where the only new thing is actually the two calls to embed here and here. And now I have added some comments, an M if the line uses monads, and an A if it's using applicative. So here at the top, we are just doing a normal list issues, and we are using everything inside a for comprehension, and then we are embedding an applicative program to traverse those issues and get the comments for each. And we do the same for the nested traversal below. And as you can see here, there are two applicative programs embedded. Okay, so now to the moment of truth. We have done a lot of work. Let's see if that all pays off. And what do we expect from running this program now? We want to have parallel execution where possible. And we do not want to have any duplicate requests for logins, because we are using our optimizing interpreter. Okay, so it's running the same program as the one with the halting opportunity, but now it's again running SVT and list issues, and it does all the get comments in parallel and all the get users, and it's already done in like 5 seconds instead of over 40 or something like that for the other program. Okay, so revisiting our program and the execution of it, it's very convenient because we could mostly reuse existing parts we already used for FreeMonads or free applicatives, because we are always defining our ADT and our natural transformation. And the result in our case was an interpreter that executes each of the stages in parallel, but we can still use monadic power to chain in our DSL to chain effects. And we still avoid duplicate requests for usernames using our static analysis on free applicatives. Okay, so to summary, we have written a small DSL creating the GitHub API. We convert a DSL using free monads and one using free applicatives. We saw the parallel execution and the static analysis advantage using free applicatives. Then we regained monadic expressiveness, because otherwise it's kind of boring what you can express in your programs. And then we combined everything into an interpreter. Okay, that's it from me. Are there any questions? Okay, so no questions, then thank you for your attention.